All right. So we're going to be doing problems involving the equilibrium of a weak acid. Most acids are weak, right? There's only 6 that are strong. And so because of that, they dissociate partially and they find an equilibrium. And we've learned KEQ, like general equilibrium. We've learned KSP, solubility products, equilibrium of solubility products, which would apply to like strong acids because they dissolve completely. So we would use like solubility product equation for that. But for a weak acid or weak base, either one, this applies to both. We have a special formula where we do products over reactants, and then there is a constant. So you can see here in this first problem, the constant's listed there. In the second problem, the constant is listed as well. Oh, I just realized these are both acetic acid. The constant will be given, or you'll be given enough information to calculate the constant based on the expression. So for an acid, the constant, that's K sub A. K sub A stands for equilibrium of an acid, and then K sub B stands for equilibrium of a base. You can see that over here. This is the only new formula we're adding. All the rest of these we've dealt with quite a bit now, but there's one more formula, and it's this one. And so if you take the equilibrium constant of the acid and the equilibrium constant of the base, again, weak acid, weak base, together, multiplying together, they equal 1.0 times 10 to the negative 14. Sometimes that's noted as, here, I'll write it over here. Sometimes that's noted as, well, I mean, a lot of times. So if you guys start Googling, you're going to see this, but K sub W, standing for water. So, okay, so our Ka expression, or Kb, again, is the concentration of the products over the concentration of the reactants in our dissolution. All right, so number 1 says find the pH of a 1 molar acetic acid solution, and it gives me the Ka. So I'm first going to write acetic acid. So acetic acid is the acetate ion, the C2H3O2, with a -1 charge. So when it becomes an acid, we just need 1 hydrogen on there. So when it dissociates, I'm going to write this over water. So you can write the H3O plus if you want, or you can just write H plus, the shorthand. It's up to you. But those are the 2 ions that it creates. So when we're doing equilibrium problems, we typically create an ICE chart. So ICE is like an acronym. ICE, the I stands for initial concentration, the C stands for change, and the E stands for equilibrium. So I can see that my question up here says find the pH, and it gave me the concentration of acetic acid. In order to find the pH, I know I need the concentration of H+. It didn't give me that. It gave me the concentration of acetic acid, but because acetic acid is a weak acid, it doesn't dissociate 100%, so we know that those are not equal to each other. We actually need to find out what it is. So I'm going to fill in my ICE chart. My initial concentration of acetic acid is 1.00, and I do not have an initial concentration of my hydronium ion or my acetate ion. My change is whatever I lose from here, I'm going to gain in each one of these, right? So if I dissociate part of my acetic acid, that acetic acid part becomes the ions. So I'm just going to label those all X. So what does that make my equilibrium? Well, that makes this equilibrium for my acetate 1 minus X. That makes my hydrogen ion, my hydronium ion, X, and it makes my acetate ion X. Well, with weak acids, we, for the purposes of this class, are going to make an assumption here that this change is too small to have an effect. So basically, like due to sig figs, we're going to assume that whatever number it is that the hydrogen is, when we subtract it from 1, because of sig figs, we're still going to get 1. So that's the assumption we make. So when I write my equilibrium expression, I have Ka, which, we have a constant. My Ka is 1.7 times 10 to the negative 5. And that's going to equal the concentration of my products. So that's x times x, or x squared, over 1. Because again, I'm going to assume that that subtraction is too small. So I'm going to solve for this. So x squared is going to equal 1.7 times 10 to the negative 5 times 1. I said x squared and then I didn't write it, huh? Okay. Times 1. So I'm going to solve that. I'm going to multiply that out, take the square root, and I get x is equal to 0.00412. And that is my concentration of my H+. So just to go back real quick and reiterate, remember how I said that this was too small over here? So if I took that 0.004212 and I subtracted it from 1, I would still get 1 here because of sig figs. So that's why we made that assumption there. Okay, this isn't, however, our final answer. Our final answer is going to be pH. So my pH equation is the negative log of my hydronium ion. So I'm going to plug that into the calculator, and I get a pH equal to 2.385. So that's my pH of the acetic acid. All right, next problem. So that's sort of basic. We use that ice chart, we find a pH. You could use that ice chart to find a concentration, which would have meant maybe I just stopped like right here, and maybe that was my final answer. I could ask you for further, or I could, maybe if you had a base and you found the OH concentration, you'd have to plug that into POH and then subtract to get pH. So there's a lot you can do there once you get into the hydronium and hydroxide ion concentrations. But the ice chart is kind of what you use to find that. All right, so this next one is a little more extensive. That's why they're separated on your worksheet. This one is under the word problems. And it's because the whole point of talking about a weak acid and understanding that they don't dissociate totally is understanding how much they do dissociate. So all the rest of the problems on this worksheet do ask you to calculate the percent dissociation. So the questions are going to be very similar to what we just did, but there will be an extra added step of calculating the dissociation, the percent dissociation. All right, so I'm going to go ahead and just write down my acetic acid one more time. We do the arrow going both ways just to show that it's at equilibrium, or that it's finding equilibrium. And so this time it says to determine the concentration of acetic acid. So I don't know my concentration of acetic acid here. And it says that my pH, so if you measure the pH, it's 2.2. Well, just as a reminder, the pH, sorry, started to write pH and then wrote negative log. pH equals the negative log of the hydronium ion concentration. So I need this hydronium ion concentration, which is going to come from here. I could set up an ice chart here. It's not exactly helpful when you don't have an initial concentration, so I'm just going to show you what that would look like. I still have 0 here. I don't know how much I'm starting with. That's what I'm looking for. I'm still subtracting the x, still adding the x's. But the difference here is I have a question mark still. It will be minus x, but remember we assumed that that's too small. But instead of making my hydronium ion concentration and my acetate ion concentration, instead of making this x and x, we actually have that concentration over here with our pH. So I'm going to do 10 to the negative 2.2. That'll equal my hydronium ion concentration if I rearrange that pH equation. And that means my hydronium ion concentration then is 0.006. I know I'm going to need 1 sig vig because my pH had 1 sig vig in it, so I'm just going to do more than that. So I'll just stop there. If that's my hydronium ion concentration, I know that that is also my acetate ion concentration. Okay, so now I can use my Ka equation, this one up here, right? I can use this equation to solve for that initial concentration. So my Ka is 1.7 times 10 to the negative 5. My products go on top, and that is 0.0063. There's 2 zeros there. 1. I hate writing that out. You guys can totally write it in scientific notation. That's how I would prefer to do it, but I just wanted to show you. And then I'm going to square that since I have it twice. And then this one is what we're looking for. Okay, so when I put all that into my calculator, I get my acetic acid concentration to be 2.34. Again, I need 1 sig fig, so that means that it equals 2. Okay, so there is my answer for the concentration of acetic acid. Now it does ask me for a second thing. It asks me for the percent dissociation. So how we find percent dissociation is a fairly straightforward formula as well. I'm just going to shorten that. So my percent dissociation is the hydronium ion concentration. So I'm just going to write H plus up here over the acid. So in this case, the acid is acetic acid, so I'm going to write that. But if you looked in the book in chapter 18, I think it gives you a general formula where it puts H plus on the top and then it puts like HA on the bottom, meaning like a general formula like any of the acids. And then we multiply it by 100 to find the percent. So that is my hydronium ion concentration is 0.00631 over my acetic acid ion or solution concentration of 2, and then times 100. So that into my calculator is 0.3155%. With proper sig figs, it would be 3%. Or 0.3%, 0.3% dissociation. All right, well, that's it. You have a few more problems to do, so let me know if you have any questions.